Okay, now let's go back and take a look at how does this have to do with the male-female problems, and why do we have this? Remember, we said that we take a look at, we cannot get normal development by adding 2 sperm nuclei or 2 egg nuclei. You have to have 1 sperm and 1 egg nucleus. When you take a look at the methylation patterns of egg DNA and sperm DNA, you find that the methylation patterns are radically different. In the egg DNA, certain genes are methylated and thereby repressed strongly, but they are not methylated in the sperm nucleus. In the sperm nucleus, certain genes are strongly methylated, repressing their transcription, but their sisters in the egg nucleus are not. So, the egg nucleus, we have shut off some genes pretty tight. They're not going to be transcribed, or at least not without a great deal of difficulty. In the egg nucleus, we've shut off, or rather, they say sperm or egg? Sperm. Oh, okay. In the egg nucleus, a different set of genes are shut off. If you have 2 egg nuclei, certain genes are completely repressed and you can't really turn them on again, at least not without tremendous amount of difficulty. End result is misdevelopment. If you have 2 sperm nuclei, a different set of genes are strongly repressed, and then again, you get misdevelopment. But if you have an egg and a sperm nucleus, there's a balance. Genes that are repressed in the egg nucleus are not repressed in the sperm nucleus. Genes that are repressed in the sperm nucleus are not repressed in the egg nucleus. So you get a certain amount of transcription of all these different kinds of genes, and you get normal development. Now, why did that happen? Why do that? It's suspected in evolutionary terms that this is kind of an evolutionary battle between the sexes. Okay, yes. Yeah. Now, we see this a lot of times in evolution. What males want, everybody, the name of the game in evolution is to try to maximize the passage of genes to the next generation. You want reproductive success. Now, the thing is, if you're a guy or a girl, how you achieve that differs quite a bit. For us guys here, the few of us that are here, how do we maximize our reproductive success? We inseminate as many women as possible. Don't tell my wife. She'll kill me, Okay. Okay. Our thing is to try, if we, it doesn't take much effort to make sperm, right? Sperm is nice and cheap and easy to make. I mean, I make enough a day to repopulate half the United States in one fell swoop. No, I don't get the opportunity to do that. My wife won't let me. She's not fun. She would kill me if she sees this lecture. But anyway, at any rate, okay, most organisms, males invest very little in parental care. That's another kind of thing. So I don't have to worry too much about raising babies. They abandon the kids and stuff. It happens down in the state an awful lot. I see this all the time. So it applies to human beings in the southeast as well and in some other places. But anyway, okay, so what's going to happen? Your main thing as a male, try to inseminate as many women as possible. Your big problem isn't so much making sperm or parental care. Your big problem is trying to compete with other males, because usually they want to do the same thing you do. So you get many organisms. You have polygamy. You have one male and a harem. I just saw something. It was one of those BBC Nature documentaries, and here they have these huge 3 or 4 ton elephant seals, and the biggest and strongest male gets all the ladies, and then everybody else challenges them. They have these brutal and sometimes quite dangerous fights. Occasionally even kill each other to try, if I can whoop your butt, I get all your women. It's like a fraternity. Sorry about that. Okay, so that's the male way to reproductive success. Basically, try to inseminate as many women as possible and prevent other men from doing the same thing. Now, if you have a female, you've got totally different things. Your reproductive success is maximized. You cannot make too many eggs. You can't make hundreds of millions of eggs in a single day, right? Okay. Right. Yeah, imagine what you look like. Oh man, I got the. Well, have you ever seen a gravid female reptile or amphibian? I mean, a good portion of the body cavity is this huge egg mass. So yeah, that would be, that wouldn't look too appealing, and it would be awful heavy to carry all that around. All right. But at any rate, okay, so eggs are difficult to make. They have to do all the heavy lifting in terms of development. Second thing, in most organisms that exhibit parental care, it's the females that do the lion's share of it. Now, there are exceptions to every rule, okay? This is a general kind of thing. Usually the females get stuck with most of the parental care if there's any at all. And even if there isn't, you know, you're a female turtle, what you gotta do? You gotta crawl up on the beach and worry about large predatory mammals, worry about, you know, poachers, human poachers, worry about getting run over by somebody's beach buggy and stuff like that. You crawl all the way up on the beach with your 30 or 40 eggs, dig this nice pit in the ground, lay your eggs, cover it up, and finally get back to sea and hope you made it out alive. And then you abandon the babies. But it still takes time and effort. Now, so what females have to do, they got to get the best mate or mates that they can find. They got to pick the best one. They got to pick the one that really macho man, you know, that kind of stuff. So they want to do that. They also, and if they have a chance, maybe they can cheat a little. They find there's a lot of cheating in even animals that pair bond. That, you know, a female will often, she gets a chance and finds somebody that's even Mr. More wonderful than her current mate is, she'll slip in a good shot. That happens. Oh yeah, they found that out. They pair bonding, the vast majority of pair bonding mammals, they have a cheating rate, genetic studies, now we can do this kind of stuff, they have a cheating rate of about 15%. There may be something to that number because there was a comparable study in a free clinic in Seattle, Washington some years ago, and they found that about 15% of the children did not have the genetic father that supposedly was supposed to have. So that rate may actually be something that's kind of almost universal with pair bonding mammals. And I hear plenty, oh, it's terrible. I hear plenty of tales from students, ex-partners, and things like that, you know. I hear all these tales, and it's basically the same kind of thing, except they get caught, you know. Just ask Arnold Schwarzenegger, you know, Elliot Spitzer, and things like that, and Jonathan Edwards, and all those kind of famous people, and there's a former president. Okay, but anyway, so you know, the evolutionary, not only do you have to be very selective about mates, because you don't have that many eggs to spare. Making eggs is difficult. You may have to raise the kids. That's always a pain. Okay, so you got to go for real high quality and get the best mate you can find. Genetically the best, the strongest, the most successful. So you'll get his genes, and your kids are going to grow up to be nice and successful on the range. Like, you know, think of the Bushes, right? You have former president, son that probably would have never gotten to Harvard, except for, or to Yale, except his father was in there. He would have had the grades for it. And then all these connections and all this kind of stuff. And then what happens? He ends up a president of the United States and runs the whole thing, you know? Okay, but anyway, at any rate. Okay, so you have that. The other thing is this, too. And this is especially the case with mammals. You're incubating an embryo, in fact, usually more than one embryo, inside. Now, for the guys, it's to your advantage, especially if you have internal fertilization, internal development, stuff like that. If your species has at least some level of internal development, if you're a guy, it's to your advantage to get those embryos to develop as rapidly as possible. Get big and strong before you're born, or whatever the case is, or hatch, whatever the case is. You want your embryos to become big and strong fast. Now, it doesn't particularly matter if that is going to you, the guy, it doesn't particularly matter if that's going to be tough on the woman, or deleterious to the woman, or even damage her future reproductive success. As long as your genes are in the next generation, the heck with her. You know, you're going to abandon her anyway, so, you know, she gets to raise your kids and all of this. I know it sounds cynical, but most animals do this. I say, I love it. I love it in the human population, too. Yeah, I mean, I've heard plenty of tales over 20 years and stuff from friends, from former students, from current students, that kind of stuff. But anyway, you know, your advantage as a male, you want that embryo to develop big and strong as possible. And the heck with how it's going to affect your former partner's future reproductive success. As a matter of fact, you'd rather not have it. You'd rather have her carrying embryos that had your genes, and you don't want somebody else to do it later on. So that's your advantage. Now, if you're that's your strategy. If you happen to be a woman, the ladies here, okay, you got this guy, he's great, you know, he's got good genes and stuff, but, and I'm gonna have his babies, I'm gonna even raise him and stuff like that, you know. Even though this creep left me right after 2 minutes after the act and left me looking for somebody, cruising for somebody else. Okay. Evolutionary biology can be a lot of fun. All right, so we got this. Okay, now, you do not, as a female, you do not want to damage your future reproductive success by having embryos go really big, really fast, use up your nutrient sources, debilitate you, make you tired, make you more prone to be more in danger of getting eaten by something or whatever the case is. You want to stay healthy and strong so that when you're taking care of these kids, you get to find somebody who's even better than that creep that just dumped you a year ago. Okay, so you want to keep your reproductive success intact because maybe somebody better is going to come along. So you don't want that embryo to grow too fast. You want to slow it down. So you make epigenetic changes in your DNA that are going to promote that. They're going to slow embryonic development. Meanwhile, the guy who wants the embryos to develop as quickly as possible and get as big and strong as possible in an early stage, he don't care what happens to mommy, right? He dumped her. As long as she brings forth the young and does whatever parental care is needed, her future reproductive success is no concern to him anymore. So he wants his embryos to grow big and strong, and when they're finally born, or whatever the case is, they're a muscle man, and they can go and forage without problems, they can avoid predators, all that kind of stuff. So, the two different evolutionary approaches to reproductive success have been translated, even at the molecular level, into different methylation patterns of DNA. So the guys and the ladies have a constant evolutionary battle. And kind of like a lot of couples in real life, you know, guy wants to do one thing, partner wants to do something else, and somewhere looks at two different things, and somehow at least, you know, one of two things, they come to a compromise. Okay, we kind of give in a little bit, and the other side gives in a little bit. That may actually work quite nicely. Either that or they go to the lawyers. Sometimes happens. But in all seriousness, when you have the egg genome, the egg nucleus, and the sperm nucleus, it's kind of a molecular compromise. The embryo doesn't grow too fast, and the embryo's development is not repressed too much. So you have a viable compromise that leads to normal development. So in this case, kind of like a lot of good couples, a big conflict in future goals and how to achieve them ends up with a synthesis that works and a compromise that works well for both. And that's what we see now in methylation patterns. Because we're going to see when we come back on Tuesday, DNA methylation is not the only epigenetic change that can happen. We're going to see some more in the roles of histones. Now we're realizing histones are involved in epigenetics in a big way, and a lot we still don't understand. So we're going to see that when we come back, and you guys take care. I'll see you guys on Tuesday.